Hi, and welcome to another Autodesk Fusion 360 tutorial. My name is Edwin Robledo. I'm part of the community team as well as part of the tech marketing team. And with us today is Jorge Garcia, which also is part of the community team. And we do quite a bit of support as well. So you'll find this on the forums, or if you send us any emails, uh, it's quite possible Jorge, myself, or our colleague out of Germany, our friend out of Germany, Richard Hammer, will be addressing your questions as well. So, Jorge, last week we went through the whole process of making the schematic. We found out how to actually access the electronic platform in Fusion 360, as you see here. Click on the pull-down menu. It says here, brand new electronic design. This is how you actually open it up. This will actually bring you to the electronic document. And from the electronic document, you could go ahead and launch a brand new schematic. Once we define some once we place some components and define some connections, we're kind of completed and answer some questions from that point on. Now today, we want to move on from the schematic over to the circuit board. And we're going to just go ahead and teach you how to be able to do that. So from the schematic, we're going to go here where it says, right here, where it says switch, as you can see here. I hope you don't mind. I like using my little arrows here, as you can see right there. It's going to go ahead and let me switch over to PCB document, as you see on the tooltip. It will just take a few seconds, and now I'm in the circuit board layout editor of Fusion 360. As you can see, the interface is quite similar. Now the design manager and some inspector and the selection filters open up down here. It looks a little different, but if I go ahead and minimize these, you'll see that the interface is actually very similar to the one in Fusion on the schematic editor. A default board outline will show up, which is approximately 4 by 6 inch board size. And on the right-hand side, on the bottom left-hand side of my screen, you'll see the components. These are all the components that actually showed up that were used on the schematic editor. I'll go ahead and just kind of do a group here. That way you could see the connections. These lines that you see here, these connections between the components were actually the connections that were defined when we were in the schematic editor. These connections that you see here. So you could see that in the schematic, I'm using symbols for our components. But now when we're working on the board layout editor, we're actually working with the physical aspects of it. Now the board outline, of course, is way too big, as you could see. I'll go ahead and click and drag just to be bringing in this board outline. Just make it a little smaller. Really want to stay kind of close to my 0, 0 of my page, and that's actually defined by this crosshair that you see in the bottom here. But you always want to be working on the positive quadrant of things. There's a reason behind this. If you generate a pick and place machine, or when you generate your manufacturing files, it's recommended that those files always have positive coordinates, and they're going to be based on the placement of on the actual circuit board. So that's why you see me working on the positive quadrant to right to grab that outline. And I'm going to now take the one from the top and bring it down a little bit. I don't really have to be highlighting the move command. It's not necessary because the group command, as you can see, yes, as we did on the schematic, is actually our default. So every time that there's no command active, the group command becomes automatically active. I'm just going to do a zoom to fit. As you can see, this is our board outline, and I have my components. The first step you should always do when you're going to start working on a circuit board is to run DRC. DRC stands for Design Rule Checkers, okay? Design Rule Checker, and this is how we're going to set up our environment to make sure that our board is manufacturable, okay? That's basically what it is. Now, Fusion 360 already has a setup of DRC, which are very conservative. Therefore, if you stick to our parameters, it's quite possible that your board will be manufactured. But let's just go over them really quick. So I'm going to go over here to rules, DRC and ERC up here, right there. You know, George, I love my arrows. So right there. I just find that it really puts the point across and that people don't have to be fetching for my mouse cursor. So I'll click right here where it says DRC. We're going to be hosting webinars, yes, based on DRC, because there's a science behind this. So I could, if I'm working with a manufacturer that has a set of DRCs that are compatible with Fusion 360, I could just click here on load and just select the DRC file that they have available. The DRC file actually has the extension DRU. It's quite possible that they may have it for Fusion 360, or they may have it for Eagle, the DRU file. Fusion 360 is compatible with the Eagle DRU file, so you could load those. Now, on the Layers tab is where we're going to set up the amount of layers that are going to be used in our design. In our design, we're only going to go with 2 layers, but I just wanted to let you know that you could actually work with 4 layers. Now, please notice that when you're working on this platform, we're always working from the outer layer to the inner layer. So we have layer 1 is on the top and layer 16 is on the bottom, as you can see here. Now the next set of layers, with another next pair of layers, is going to be layer 2 and layer 15, as you can see here. So it's always going to be working from the top to the bottom, as you can see. Let's go here and there and there. Do one more example. If we were going to set up a 6-layer board, you'll notice that it goes 1 to 16 all the way to the bottom, 2 to 15, and 3 to 14. Those are our pairs. This straw that you see here looks kind of like a straw right here. As you can see, this little gap that we have here is the transition of our vias. In other words, our points of transition on the circuit board when it's traveling a signal between a layer to another layer, it's actually going to be going using vias that are actually traveling the entire board.
And just for a practical consideration, typically this is the cheapest stack up you can get when the vias go through the whole board. If you get more sophisticated and have vias that only span certain layers, then the price increases pretty dramatically. So if you can, you want to try to see if you can make your design using just through hole, because if you have any type of depth controlled vias, then things become very expensive. Some designs need it, but make sure yours is one of those.
Thank you, George. Appreciate that. Now, another parameter that you want to check on your DRC besides your layer stack is your clearances. We're using clearances of 6 mils throughout the entire board. In other words, between each trace, we have 6 mils. Between the connecting points of the component, which are through hole or surface mount, we're actually also using 6 mils. And all throughout, you'll see that we're using 6 mils throughout for our pad to pad, vias to vias, and so forth. The nice thing is that these parameters are respected by the outer router, and when you're doing some manual routing, which I will show in a few minutes. The distance is, and this is the last one I really want to cover, is the distance that's going to be left from the outline of the board to any component. In other words, if anything violates, it's under 40 mils, it's actually going to flag that violation. Now, please remember that it's not going to stop you from not doing the action, even if it violates DRC, but it will warn you. And I'll show you how those warnings actually are going to come up on the design. Now I'm going to change this outline to 40 mil. This is really conservative. So I'm going to bring this down to maybe like half the value. I'll set it to 20 mil. Some other parameters are here available, but I'm not going to cover these for our example for sake of time, because we are going to be doing some webinars, yes, on the DRCs by itself. I'll click apply and I'll click on cancel. I don't want to use a check yet because I haven't began laying out my board. Therefore, I don't need it to check my design based on my preferences on the design rule checker. So I'm just going to hit apply. That way it actually sets those as my parameters, confirms that those are the parameters I wish to follow my design. I'll go ahead and click on cancel. That way I could return to the board layout editor. Now I'm going to start selecting components and actually putting them inside the board outline. As you could see, the inside of the board has a slightly different color than the document outline as well. So this is my circuit board area. Now, since the default command is always group, I can now click and hold on the origin or the handle of the component and actually select it. Well, in this case, I actually have a trace there. It's in my way, so it's not letting me grab it. So you know what? I'm going to just show you a little bit of how to use the selection filter here. Let's go ahead and enable this. And I'm going to tell it that I want it to allow me to go ahead and select components. So let me just find the components here. Should be my selection filter should be device here. I'll go ahead and hide this one more time because I no longer need it. Now, when I start selecting components, it will filter out anything else other than a component. Now I could click here and select that component, as you can see. I'll go ahead and place one. Now I just go ahead and start grabbing my other components. Now those connections that you see, those white lines that you're seeing there, I'm at a very coarse grid. That's why it's actually kind of like being so jumpy like that, you see? Please remember that on the schematic, we recommended that you always work on a 0.1 inch grid. So when it comes to the circuit board, you do not have to follow that rule. I'm just going to go ahead and lower my grid. That way I could fine tune my placement. I'll go ahead and click on the grid icon on the top toolbar, as you can see here. And I'll go ahead and I'm going to go ahead and lower this to 5 mils. And click OK. Okay, now when I start selecting my components, you'll see it. Now there's an observation I want to do here. As you notice, I was moving this component. It was getting really close to the edge of the board. You notice those hatch lines that are showing up there? Those hatch lines are just letting me know that DRC, there's a violation at that point. That's a DRC violation. Just letting me know that if I place it there, I'm going against the criteria that I already had set in DRC. Therefore, if I actually move it back away from there, the DRC by default is active live all the time. I'll go ahead and start moving some of my components over into the board outline. I'll just use the zoom to fit. And I'll continue to click and hold. Remember that I've set the filter to only select devices. Therefore, it's going to ignore anything else. I'll bring in my capacitor. Now, I did a left click and hold. I'm actually holding my mouse cursor right now to move this component. If I wanted to rotate it, I could just do a right click and it'll rotate it in increments to 90 degrees. As you can see, it's going on here. I'll go ahead and move it to a position where I actually want it to be placed. And I'll just release my left mouse button. That way it actually places it where I want it to be. I'll continue moving some of my other parts over as well. I could go ahead and define a group and actually bring all these as a group in here as well. And I'm just going to bring in my LEDs. I'll bring this one, put it up here. And I'll just bring this one down here. I'll do a zoom to fit. That way you can see what I've done so far. Now, please notice that the attributes, these are called the attributes. So this is the name, the reference designator of the component. And this one that you see here is the attribute for the value of the component. Now, when there's not a value assigned to the component, it actually by default puts the name of the device that it has in the library. Okay, so all these names that you see here, it's common for you when you're working on a circuit board that you don't really need these when it comes to this type of component like the LED. You do need them for the resistors, as you can see, R1, R4, R3, and R2. They all have their values, and those are important to be able to see those. Okay, but I could actually go ahead and move this part. I'll click and hold again, move it here. I'm going to go ahead and reset my filter. That way it lets me select those attributes that I'm not seeing right now. Let me go ahead and turn this on. I'm going to go ahead and reset. That way I could accommodate these as well. So let me just go ahead and do this here. I should be able to select these guys only by themselves. There you go. Select that one, put it there. I'll do the same for the one on the bottom. Go ahead and put that there, right here as well. And I'll put put it there. And I'll select. I guess I defined it as a group. Okay, we'll put that one there as well. Okay, now I'm going to go ahead and do a zoom to fit. Now there's just one really neat feature that I like to show you. It's called alignment. So if I had, and yes, today I got a support call regarding this today, Jorge, because somebody had like 150 LEDs that they're working on their design. So they wanted to be able to just line them up. So I'm going to go back to the design tab as up here on top, as you can see right here. I'm going to go back to that tab. I'm going to go back to that tab, and I'm going to be using the align tool that we have right here. I'm sorry, the align tool, this one right here, align tool. Okay. So I'm going to first define our group. So I have the group command active, as you could see. I'm going to define my group. Now I'm going to have the align tool, turn it on. As we can see here. Oops. I have to reset, I guess I have to reset this here. And let me do my group. Okay, and now I can use the alignment tool. Now you'll notice that they have multiple alignment options going on here. So in this case, I actually just want to line them up. Now imagine that each component has like an imaginary box. So depending on the size of it, it actually creates a box which is kind of like the boundary area of each component. I just want to line them up horizontally to start off. Okay, I want to line them up horizontally, as you can see here. Now the option I selected is horizontally based on the component that is at the most bottom. So I bring everything else, it brought it to that level, brought all those. Now if I want to space them evenly, if I want the space to be evenly, I should be able to click here. And let me see, tooltip didn't show up, but now they're all spaced evenly, as you can see. Now I just go ahead and define a group. That way I can just move it, because I just find them, they're just too close to that. That, and I'm going to go ahead and move this back up a little bit. Oops. And go ahead and click OK. Very well. Let me do a zoom to fit. Okay, and this is more or less how I really wanted my design to kind of look like a little bit. Now, as a matter of preference, I just like having the attributes kind of like all be lined up properly. That way I can look at the board and actually read my component attributes or the reference designator. So let me just go ahead and grab this. Put it right there. You can see there. Okay, and I'll just grab this here. Okay. Now, all these connections, they're referred to as signals. Just to let you know, when you transfer over the schematic over to board, they're referred to as signals. Now, this whole setup that you see here, this everything that you see, all these connections, the term commonly used for all this is called rat's nest. So we're in rat's nest mode right now. So all the connections, they don't have a trace. Also, these connections are also referred to as air wires. And I think they were the term air wires because they, as I move the component, as you already saw, they kind of like stretch and contract, as you can see. The connection is never lost because I don't have a defined trace for it, yes, as of yet. Okay. Now that I'm going to start defining some of my connections on my board, you'll notice that I do have the option of showing the signal name on the pads. You're noticing that the signal name shows up on the center of the pad. So this connection right here is actually driving V+, and these have $3 and so forth. I should be able to see a set of them carrying ground, most probably. As you can see here, this is actually carrying ground. You'll find this if you click on your name and you click on preferences and go to the electronics tab, to the electronics sections. These are the different preferences that you could set up there. That's where I have it right here. Okay. Now I'm going to go ahead and do a zoom to fit. And at this stage, I just want to go ahead, zoom to fit. Now what I want to do is start routing. Now that I've defined, place my components, first you define a layer stack up, okay? That's what we did first. We did the DRC, we went to layers, and we did some modifications to our sizes as well as reviewed our clearances that we wanted to use. Now I'm going to start using the route command, but before that, I want to optimize my connections. And remember I was using the term rat's nest? Well, that's what we're going to be using. It's called rat's nest. That's the name of the command to optimize my connection. So in other words, if you're doing the same design together with me, it's possible that these results might be slightly different, might slightly have a different path, but doesn't mean it's wrong. Okay. So the rat's nest command, what it does is right here, it says, besides pouring polygons, which I'm going to do in a minute, it actually will optimize the connection. So you may see a slight difference of how these IR wires are actually traveling here. As you could see, it actually did a slight modification. It's very subtle, but it actually did a slight modification. One more aspect I would like to, before I start routing, is I want the LEDs actually to appear on the other side of my circuit board, because I am only going to be using these components on the top layer, and then I want my LEDs to appear on the other side of the board. To be able to accomplish this, I could do a right click on the component and select the option mirror right here. I could accomplish the same thing by clicking mirror command up here on the top toolbar as well. As you can see, it automatically activated, and click on the component. Please notice that the pads, the landings, where the components get soldered onto the circuit board, actually got turned into blue. This is an indicator, yes, letting you know that this component is on the opposite side of the board. In this reference, we use the color blue to refer to the bottom side of the board, while we use red for the top side of the board. That's how you know the difference between one layer and the other one. Okay. Now let's start doing some manual routing techniques here. I'm going to start with the most basic one. Manual routing is maybe where we're going to live at. So manual routing, actually I got to fix these. Hit escape, get rid of that command, and start moving these reference designators here. And actually, I got to hit escape to separate it from the component. There we go. That appears on the bottom of the board. I'll go ahead and select this one here. That's going to appear on the bottom of the board as well. Okay, so we got a 2-layer board. We got it going. Now, the routing tools are going to be located right here. These are the first ones I'm going to start with. There's some more, but I'm going to actually be starting with this one right here, the manual route command. Now, I would have to admit that it's common for you to manually route your board. You really want to try your best to kind of stay away from the auto router. The auto router does a great job, but it's never going to do a job as well as you doing it manually, because you just have a different insight of how you want to do it. The auto router basically is going to do its best to do 100%, but it's not going to really take the aesthetics and other considerations necessary for your board. Some considerations may be, like the load on a board, the load on a signal, I should say, and so forth. Now, I'm going to go ahead and right here, you see where it says manual route, which is assigned to this icon right here. I'm just going to click there. And I'll start routing. I'm going to start with something simple. I'm going to start with this ground symbol that we have here. You zoom in a little bit on it that we can see it. When I activate the route command, I'll go ahead and click here. As you can see, kind of X showed up when I clicked on it. Okay, as you can see, that's the starting point of the route. Now, there's a default thickness actually being assigned to my trace, and this default thickness that you see on the trace is based on what I have in DRC. Okay, I'm going to hit escape really quick. That way I can just show you that really quick. So I'm going to click on DRC, and I'm going to go to the sizes tab here. So the minimum width I'm using under the sizes tab is actually 6 mils. So when I start manually routing, it's going to use 6 mil or greater, but it's going to start at 6 mils. Now I could change that value to a greater number. If I force that value to be smaller, it's going to bump it up back to 6 mils. Okay, so it's always going to go to 6 mils by default, because this is just the setup I have here. I got to go smaller, but it's always going to say 6 mils. This minimum drill that you see under sizes right here is the size of the hole that is going to be used for your points of transition for your traces. When they're traveling from one layer to the other one, it's going to use at least a drill hole size of 0.35 millimeters. That's just what this is saying here. Okay. So let's go ahead and go back to our route. Let's go back to design, click on route, and start routing. Now, this is a surface mount component. A surface mount component is a component that sits on one side of the board only, either on the top or on the bottom. In other words, it doesn't have a hole. It doesn't have a footprint. It doesn't have no presence on the other side of the layer. It actually sits on top of the board, on the surface of the board. Now, as I manually route, you notice that the trace is kind of in an outline mode. That's just letting me know that that's the one I'm currently routing. I've learned of some users that actually change this parameter because if it's a really dense board, it's hard to see it. But on this simple board, and I like working usually with the defaults all enabled. So as you can see, that outline on the board, and it's in red because I'm on the top layer, as you can see here. I'll go ahead and continue routing, and I'll go to my next pad where I want to route. Please notice that we get that X right there where we route, where it wants to end. It's snapping to that end. You don't hear it on your end, but now when I left click to actually place that trace, I actually hear a little sound, like a confirmation sound on my earphones, okay? That's to let you know. You could continue just routing as you want to here. I could go this way. Now, we have something called obstacle avoidance actually enabled, and I'll show you what that means. It's right here. This is all. That parameter that we have here is referred to as obstacle avoidance. Let me highlight it, that way you can see it. Right here. That's that parameter that we have. This one is my active parameter. It's the default one. What that means is that when I'm manually routing, when I'm doing any route, it will avoid DRC violations, any design rules violations. So as you can see, it doesn't let me go onto the top of that part. It's just totally avoiding it, as you can see. Now, if I want to have full control, and there are times that you do want to have full control, I could actually go here and select ignore obstacle routing, and as you can see now, I'm actually able to go in any direction you want. Now you'll notice that I have DRC live, therefore I get the hatch markings letting me know that I am going on some violation as well. Okay. Now, Fusion 360 also supports push and shove routing. Push and shove means if a trace needs to route and it doesn't fit, for some reason, because it's really tight, it will actually try to create and plow a path. I could activate push and shove right here, as you can see here. And you notice as I get close to this line, it's actually pushing it away. Okay. On really, really dense boards, this could be very useful because let's say, for example, you need to make a modification to a schematic. Therefore, maybe the connections actually get modified on the circuit board, the connection. You may have already had, like, say, 75% routed. Instead of having to get rid of those traces, you actually could invoke the push and shove. That way, it kind of like plows its way and it'll move everything out of the way. Now, the distance that it's actually being leaved right there, that distance that you see there, this distance that you're noticing right here, like that distance that you see right there, that distance is actually the distance that was set up in DRC. Remember, we were using clearances of 6 mil. That's that clearance. That's where it's taking that number from. That's where that's actually coming from, just to let you know, okay? Then I'll go back to my regular obstacle avoid. Okay, so we'll just go up and over. I'm using my center mouse button to just kind of like zoom in and zoom out, and I press and hold my center mouse button to be able to pan. Okay, so I'm doing right here. When I left click, you see the difference between the portion that is already routed and the portion that is not routed. You see, so the portion that I'm routing is actually in the outline, and the portion that I already confirm its path is actually solid, as you can see there. I'll go ahead and continue routing and go all the way to the end. The air wire kind of gives me kind of a sort of a guideline of how where my end should be. So I'm just left click. That way I could change directions. And I'll go ahead and stop right there where the X starts right there. Okay, and I get a little confirmation tone on my earphones. Now, let's go ahead and let's see how we're going to handle right here. So I have to actually go from a component that is sitting on the bottom layer, and I got to make this connection to a component that is on a different layer. And this is the way we actually handle this. Remember I told you earlier on DRC we set up the via, the size of the drill hole for my via for my point of transition. And that's what you're seeing right here. Since I have the route command active, actually, that's what you see here. As you can see, the size of my drill hole, this drill hole size that we have here, is actually going to be of this size that we have right here, which is equivalent to what we had at 0.35 millimeters as well. Now, the size of the pad, the amount of diameter, the amount of copper that is going to be exposed, the amount of copper that's going to be used, which we refer to as the diameter, that's this arrow that you see here. So that's the distance from here, as you can see already, it's the distance from here to actually right here. The size is going to be automatically calculated for me based on the drill hole size. When we go over DRC, we're actually going to go into how is that calculated. Now, I'm going to start routing this trace, as we could see here. When I start routing on it, you notice that since the surface mount pad is on the bottom side of the layer, it actually is coming up on blue. It's just letting me know that I'm actually routing on the bottom side. Now, if I go all the way here, it will never connect here. As you can see, let me zoom in on this a little bit. See, it won't connect here because this pad is actually sitting on the top layer. So I can't connect to it. Therefore, I'm going to go ahead and zoom out a little bit. And I'm going to hit the space bar once. There's different ways of doing it, but I'm just going to use the space bar because I just feel it's the easiest way to do a point of transition. When I hit the space bar once, now I'm getting that donut shape via. It's kind of round. And the reason we like using round as default, because that way it looks very different than the default that we use for through hole pads, which is kind of octagonal. That way you could really tell the difference on a through hole pad versus a via. They're very similar looking. I mean, they function exactly the same, but one is a connecting point, one is a point of transition. Remember, as we said earlier, points of transition are referred to as vias. Now, it's going to automatically now go to the bottom layer. This is the 2-layer board. And I could place the via where most convenient it needs to be. I'm just going to take it to this point right here. And I'm going to do a left click to place it. You're going to notice that my trace goes to a solid color, which is a solid blue. And then now when I start moving my mouse cursor, it goes red. It's just letting me know that I've transitioned from one layer to the other layer. I've actually done the transition. I'm going to press and hold my middle mouse button. That way I could come pan. And now I'm going to go all the way to this pad right here. As you can see, the X lets me know that I am on the right layer and I'm actually at the right connecting point. I could go ahead and left click to finish my route. Now, let's go ahead and do some more routing, but let's use some different techniques now. I'm going to go ahead and click on route, and I'm going to select the option. I'm going to start with some quick route techniques. Quick route is, yes, an automated way of it actually making the decision for you to route from one point to the other point. Let me just activate this one. I use quick route here. And I'll select any of these components that we have here. I'll just use this one. It's real straightforward. And I click on it. As you can see, it put the route for me right there. I'll click on this one to see if it's able to accomplish it. Actually, as you can see, I found a path for it going around here. As you can see, I don't really like that path because it kind of like block these guys right here. So these are going to be very difficult to reach. But I just wanted you to be able to see the options for quick route. Now, if I want to get rid of a trace, what you're going to be doing is that you're going to select here this option here, what says rip up right here. As you can see, there's several options for rip up. I'm just going to go with the default one. And if I click on the trace at any point in a trace, it will actually get rid of each segment, as you could see. Now, if I want to get rid of the entire connection from one point to the other point, from one pad to the other pad, I select this option that we have here, connected copper, and I just click here, and it actually gets rid of the whole thing, as you could see. Okay, that's how one way you could actually get rid of them. Now, we do also have the option of doing multiple signals at the same time under quick route, as you could see here. So we have quick route multiple lines. We could do it by a particular signal. So let's say, for example, I selected this and I selected ground or V plus or any other signal. Anything that has that same name is going to try to quick route all of those together as well. Okay. Now I just want to go ahead and I'm going to rip up the entire board, all these connections, because the next demonstration is about using the auto router. On the quick route, you're going to see right here where it says auto router. This is an algorithm by which it will use different uh, uh, different paths and different concepts depending of your board to be able to route the board for you 100%. Now remember, and this is really, I really like everybody to remember this, the auto router will not touch anything that you have manually routed. So take advantage of that. You could do you could do manual routing for like straight line connections or anything that has to be really trivial. Go ahead and route that because and then you could invoke the auto router to take care of the rest because it's not going to really take it into consideration. Okay, so I'm going to go ahead and I brought up the auto router. Since this is a two-layer board, it actually already has a two-layer board set up, as you could see here, top and bottom. As you could see here, it's a two-layer board. I'm going to increase the effort. I'd like to increase it to medium. It just means that it's gonna analyze the board and maybe increase the amount of tries it's gonna do on the board. It's gonna do a maximum of 8 threads if it feels it's deemed to. If it feels that 6 threads is only enough, that's okay too. I'm gonna let it set the grid itself. It's going to find a kind of a common denominator grid to route the board at its best. And I'm actually allowing the topological router run, which is a slightly different algorithm within the auto router that takes into consideration more about the geometry and positioning of the components to do it. It actually does a really good job. Now I'm going to go ahead and click on continue. Now, if I wanted to do only one signal, or a few signals, I would actually click here where it says select, as you could see here. I would actually say select. But in our case, I want to do the entire board. So I'm going to go ahead and click on continue. After doing a quick analysis, it's noticed that it's actually going to do 10 runs in addition to the topological router. Now, there's many other parameters. Now, remember, the auto router is going to obey all of the parameters that have been set by the design rule checker by DRC. It's going to look at those distances and clearances. It's going to obey all of that. Okay, it's not going to get away from that. It's going to take care of that. Now, we do have some cost factors, and this is a science all by itself. Our defaults are actually work really really well, so you really don't have to mess with this. But these are just some additional factors that could be fine-tuned when you're using the auto router if you wanted to. Now, I'm going to go ahead and click on start. Yes, for the auto router to begin. Click here on start. And you notice that it starts, routing everything, and you see blue is the top, and the bottom, and red is the bottom. Now that it's completed it, as you can see, it says, while it was running, it was said running, and when it completes, it says completed, as you could see. I have several options I could select for. Depending on what's necessary for you or what you deem aesthetically correct or functional, you actually could browse through these different results. And depending where you want to go with, you could go ahead and click on end job. That way it ends a job there. I usually do my best to use the options that have the least amount of vias, but that doesn't necessarily mean it's the right one. But I just like avoiding the vias. Okay. Now I'll go ahead and select this one that has just 4 vias, which is a topological, and it's very common for the topological, the top router to have the least amount of vias. It's very common for that. And I'll go ahead and click on end job. Okay. Now that I've completed the job, all times I'll define polygons at this point. And actually, it's even a better idea to define polygons before you actually run the auto router. And polygons basically do a complete flood on the board of a particular signal. And there's a lot of benefits to that. That way all the signals reach their destination at the same time. Actually also takes care of different interferences that could happen throughout the board. They could actually be taken care of by using polygons. In our case, I'm going to try to use, I'm going to go ahead and define a polygon. And I want the polygon to cover the entire board. So as you can see, this is the outline of the board. I'm going to go ahead and right-click anywhere at the outline of the board, and I'm going to select the option Convert to Polygon. But I don't want to convert this outline to polygon, so I want to duplicate it. I'll click here where it says Copy. And I actually want my polygon, in this case, to be on the top layer. And I'll go ahead and click OK. Polygon got created. As you could see, those dotted lines right there. Let me see if you could see that. Those dotted lines are now my polygon. Now, it's quite important that you actually name your polygon. It's really important. So I'm going to click on this edge. I'm going to do a right click right here. And I'm going to go to the name option right there, as you can see. And I want to name my polygon. I want to name it. I wanted to conduct ground, for our example. I'm going to select ground and click OK. Now to have the polygon pour, because now I want to visually see the polygon. I want to see how it's going to work. I want to see it pour. I'm going to go ahead and click right here where it says pour polygons, which is the same. It's the same command that we were using to optimize all the connections, the rat's nest command. Click here for polygons, and you notice that my pour actually happened. Okay, it's keeping a 20 mil distance from my edge of the board. We actually had defined that in the DRC, as you could see. So the distance from here to here, it's at least 20 mil. And we already did that earlier on DRC. So that's the distance is being obeyed. Now this polygon has what's called orphans turned off. Therefore, if any portion of the polygon gets separated from the primary polygon, it actually does not pour in that area. And that's what you're seeing here. Did I get that right, Jorge? Is it orphans off, which is our default? So
yeah, the default is orphans off, so that they don't get filled in the little islands.
So these are orphans or islands. So as you could see here, these actually got totally avoided because they will, if it did pour there, it would actually be separated from the primary polygon. And that's actually our default. Now, another aspect that I would like to bring up here is the connections that get defined. Actually, this polygon is using a very fine wire width. So let me just go ahead and unpour our polygon. I'm going to unpour the polygon, go back to outline, and I'm going to take a look at the properties of this polygon. I'll go ahead and right-click it, and I'll go to properties. My polygon is actually using a, let me see, what is the width of this? It's using 0 width. Okay, I'm not sure why. I guess an earlier example, I was using a small width. I'm going to change it to 12 mil wire width. I'm going to go ahead and click OK. And now I'm going to run rat's nest again. That way we could see it pour. Perfect. Now, when there is a pad or a via that is conducting the same signal name as the polygon will automatically connect to it if there's enough space. As you can see, the polygon is actually connecting to the surface mounted pad component that we have, which is C1. That's one of our capacitors, and C2, our other capacitor. Now, you'll notice that this thermal is actually like a spoke. It's like a spoke-like connection. And the reason it's a spoke-like connection is because if it was a solid connection, heat would dissipate too fast, and it would be extremely difficult to solder this component, if at all being able to solder it, because heat would just spread too fast from it. So that's why you actually see that it has these spokes like that way heat would build and you could solder this component. This one is connected, as well as, of course, my battery connection right here, where I have my V plus and my ground, where I'm going to be connecting my battery. They're connected there as well. Now that I'm kind of satisfied with what I've done so far, I like going back to the electronic document and save from this point on. The reason I like to save from here is that it will cascade that. It usually will cascade the name of the electronic document. It will actually cascade it all throughout, as you could see. And I like having the same name. As you can see on my tabs on top, it actually cascades that name all over the place. Now that I've actually put the components together, I did some manual routing, it's time to run our DRC and see if we have any violations going on. So I'll click on the rules, DRC, ERC tab, and I'll click right here where it says DRC. Remember, we did apply earlier. Now this time I'm going to do a check. I wanted to check. I don't get no report because apparently I'm that good, Jorge, and I got no violations.
Yeah, if you have no errors, it won't pop anything.
It won't pop anything. So apparently we did such a good job that we did get no errors at all. So that's pretty neat. So if we did have an error, we'd get a little kind of a dialog box open up, and as you highlight each error, it'll actually kind of like show it to you. Well, now that my board is done and I did all this work on it already, it's time to create what's called the manufacturing files. Those are the files that you're going to be using to be sending to a board house to actually have the circuit board actually created. Okay. Now, to be able to do this, let me do a zoom to fit really quick. I don't know why, but I just like seeing the board of my total board. Now, the first thing I'm going to do is I'm going to click on the manufacturing tab. And I like to preview my board before I actually go to the process of creating the manufacturer files. And that was right here. It says CAM preview is right here. This is exactly how my board is going to look when I receive it in the mail from the manufacturer. This is the component side. This is the top side of the board. So as you can see, I can see all the landings where my components are actually going to be soldered with. I see the solder mask. The solder mask is that protective material that is actually going to protect all of my design components, and it's only going to be exposing, as you could see, it only exposes my landings where I actually solder the component. This is the top side of the board, and I can flip it down to the bottom side of the board, as you can see. This is now my board. I have my two LEDs right there going on, and these little holes that we see here are the little donuts are actually our points of transitions on the board. Okay, so that's actually carrying that signal that's coming out of this LED. These LEDs right here, and if I go back to the top, it's actually those are the points of transition of where those LEDs are coming from the bottom over to the top. Okay. Now that, and there's some other statistical information that is actually very useful here. I click on board here, and I could see how much routing we have, how much copper material we actually have here. We have 6 signals. Our trace width gives us some pad information, how many connecting points we have. In this one, we have this 24. In this technology, I'm only using surface mount components. Therefore, it has 24 pads that are being used. That's all the pads added to it. How many components we have, and actually will give me a stack up for the ones on the top. We have 8 components, and then we have 2 components on the bottom, which are the LEDs, as you already know. There's a lot of statistical information, which is kind of useful to know about here as well. And here it tells me how many drills I'm using. So I'm actually only have 4 drill holes, which are the 4 drills for the board, for the vias, and of the particular size of 0.35 millimeter. Imperial 14 mil, I'm sorry, for a count. Okay, that's how many vias we have. Now let's go to the CAM processor. I'm going to click here where it says the CAM export. This option. There's a couple options that we're going to be seeing here. Can you still hear me, Jorge? Thank you. Appreciate that. I kind of lost hearing myself for a minute there on my headset, so I got a little confused. Okay, now I'm going to go to the CAM export right here. This is kind of like a really quick way of creating your manufacturing files. I'll click here where it says CAM export. You'll see this dialog box will show up. One moment. Okay. It automatically detected that it's going to be a 2-layer board, as you can see here. When I selected that option, it's a 2-layer board. And it's going to create all of my Gerber files. These are all of my Gerber files that I'm going to be creating. All these are my Gerber files, as you can see there. The only different file that we have here, so we have our Gerber file for the top side of the board. We have our Gerber file for the bottom side of the board. We have our board outline. We have our solder mask, which is kind of that protective material, which is usually green that you see on the circuit board. We have our cream layers. We have our silt screen layers. But please remember that when your board is manufactured, it's manufactured by layers. So it's kind of going from the inner layers to the outer layers. It's being stacked up that way. If I'm satisfied with everything that I see on the CAM output that I'm going to have here, I select OK. It's going to ask me, where do you want these libraries, where do you want these CAM files to be located? And I can select there, and you select Save. Now I could go ahead and email that zip file that has all of my files over to the board house. And usually within, depending on the agreement you have, between a week to 2 weeks, you get your circuit boards made. That's one easy way. We call that the one-click solution. As you could see, I click there, and I basically just followed the prompts, and I got my boards made. Now I want to go through a slightly different procedure. It's a bit more manual. So I'll click on the option in the middle, which is the CAM processor. I'll click on there. And this actually brings up the CAM processor algorithm that we're going to be using. Yes, as we did earlier, you're going to notice that it actually loaded the 2-layer template. Because since the circuit board only has 2 layers, it's actually going to use a 2-layer template. My Gerber files for the top, my Gerber file for the bottom. Remember, I was telling you it's per layer. My board outline Gerber file, my solder mask file, which are only these components being exposed on the solder mask. Everything else is going to be covered. This is for the bottom. So when you generate your manufacturing files, you're not generating one file. You actually are generating multiple files, okay? So so we have our solder paste and our silk screens, and silk screen for the bottom. We also need to generate a file called the drill file. It's a file output that is actually going to give us the X and Y coordinates for all the components. I'm sorry, the X and Y coordinates for all the holes on the board. Here we're going to be generating our bill of material, a BOM, and also it's going to export what's called a pick and place machine. So if you were going to be using an automated system to have your boards populated by its components, you could actually use that file to a manufacturer. That way he could program his pick and place machine to put the components on your board for you. I'll go ahead and click on process job if I'm satisfied with these settings. It's asking me exactly where do I want these files to be located. I'm just going to go ahead and use the default, which is under Fusion 360 Electronics CAM, and I'm going to go ahead and click on Open here. Job is successful, and I'll click on Open Folder. And I can't see it here, but it actually opened up the file manager, or in my case, I'm using Mac, so it opened up the Finder to let me know where all the files are located. Okay, I actually put them in there. These are the files where they're located. And with this, we finished the process of actually working on your board, laying out your board, a few manual routing techniques, as well as generating output files. In essence, this ends the presentation we wanted to do today.